So I'm late, just distracted. Encore une fois, c'est en français la prochaine. Non. So anyway, we'll have another sequence of presentation this week by Maria. And this afternoon it's supposed to be Jeff Fremmel. I've not seen him yet. So where's Jeff? I'm hoping he's going to come. But they're not that news. Anyway, so Maria is going to explain to us lots of Schubert-y things. And it starts with a quiz. And I will fail the quiz myself. Because I'm looking at first questions and no, I'm joking. So Maria, I'm just going to say one thing about Maria. I liked a lot her blog, so that impressed me, and I'm sure she's going to do a great job of explaining complicated things in a simple way for us. So.
All right. Well, thank you for having me. Thank you all for coming for this mini course. I've got to remember I have a thing on my head here. So I'm an evil teacher, so I'm going to start off with a quiz. I'm going to hand out copies of this first page of my lecture notes that I have online. So I'm just going to pass these around, just pass them back along the rows. If there's not enough in some row, just let me know. Here. Oh. There we go. Okay. And I think I've already handed things on this side, but okay. Okay, so let me just start with some sort of logistical things. This is the first page of a document of lecture notes that I've put together for this mini course. This document is going to be updated online throughout the week as I realize that I should put things in that I said during class that I forgot to put in beforehand. It's roughly divided into 5 sections. Section 1 is going to be some background. Section 2, we're going to talk about the Grassmannian. That's basically day 2. Section 3 is going to be our first very, broad introduction to Schubert calculus. We're going to intersect Schubert varieties in the Grassmannian. And then section 4 is going to be the flag variety. So this is an optimistic outlook on what we're actually going to cover this week, of course. We'll see if we get there. And then I have another variation thing called the orthogonal Grassmannian that will do some Schubert variety in as well, some Schubert calculus in as well. So of course, the pun here is that Schubert is both a mathematician and a classical composer, but they're different Schuberts. So Schubert is in math is Hermann Schubert. He was an 18th century mathematician, but Franz Schubert, the classical composer. He would write sometimes variations on a theme, and so I titled it "Variations on a Theme of Schubert Calculus." No, it's not literal. So, yeah, we're going to start off with a quiz. Oh, and logistical things. So these lecture notes are on my website, which if you Google Maria Gillespie, you'll find my website at UC Davis pretty easily. You see the menu in the upper left is a young tableau in English notation. I'm sorry, French notation doesn't fit very well on a website. So you click on the teaching button in the young tableau, and then I have it right here for the week. You just click on lecture notes, and that brings you to this page. Sure. Everybody wants to click on the conjugate bar. There we go. Okay, we conjugated the young tableau. I mean, this is, you have to be careful with tableau because maybe it's not semi-standard anymore. I don't know, but.
You should add another French.
Oh, and then I could do a French just there, but it would overlap with teaching, right?
French.
Sure. All right. So, everybody okay with finding the lecture notes? These are, also at the end of each of the sections there's problems, and I'll probably add to those problems during the week too. So during the exercise sessions and problem sessions, if you want things to work on, they're all in this document. Okay, so you all have the quiz? Anybody missing one? Okay. There's probably extra. So what is Schubert calculus about? Well, the historical way it started was answering questions like the ones on this quiz. Just intersection problems, linear intersection problems in space. In particular, so there's very, very simple intersection problems that you've probably seen before. How many lines pass through two given points in the plane? So, all right, I'll take a poll. How many think it's A, 1? How many think it's B, infinitely many? And how many people think it's C, 1, as long as the points are distinct? Okay, that's very good. So the points definitely have to be distinct in order for there to be a line through it. But I also want to just pause here a second and talk about why I'm using C2 and not R2. Usually R2 is what we think of as the plane. And C2, you might think, well, that's like, that's like R to the 4 or something. Like, what is even a line? What do I mean by a line in the plane C2, right? So what I mean is just the solution set to a linear equation in the complex numbers. Something like ax plus by plus c equals 0, and x and y, or a, b, and c are any fixed complex numbers. So then you get a pair of complex numbers. So then, it's an easy algebraic exercise to show using this definition that as long as the points are distinct, there's a unique line through any 2 points. Okay, how many points are contained in 2 distinct lines in C2? Is it A, none, B, 1, or C? It depends on the choice of lines. What do you guys think? C. Again, C. Because the lines could be parallel, right?
So the answer is always C?
In Schubert calculus, the answer is always C. Okay, so it depends on the choice of lines. But we're going to end up changing this problem, too. We don't actually like parallel lines. We want all lines to intersect. So we're going to end up going to projective space pretty soon. But for now, let's stay in C2. Okay, let's do a slightly more complicated intersection problem. How many planes in C to the 4th contain a given line and a given point not on the line?
C.
Very good. Yeah, so the answer is B. There's going to be one plane determined by a line and a point not on the line, because I did specify here this not on the line condition, so I didn't have to say, oh, as long as they're distinct or whatever. But you'll see, you have to be careful about the distinctness and where these lines and points are. Okay, so let's go on. So you guys are doing very well on this quiz. So let's go on to problem 4. How many lines intersect 4 given lines in C3 where no 2 of the 4 given lines are parallel or intersecting? Okay, how many think it's A? How many think it's B? And how many think it's C? How many people have no idea? Raise both hands. All right, cool. Great, so this is a lot harder of a question that you probably haven't seen before. So let's imagine it. You have 4 lines in space, and you want to know how many fifth lines pass through all 4 of them. So this is one of the questions that Hermann Schubert was sort of first interested in, these kind of harder questions of intersection. And the way he approached them was to say, I'm looking for an eraser, but I'll just go to the other side of the board. I think they're behind the projector. But, so the way he approached them first is to say, well, let's say in a degenerate case that 2 of my 4 given lines intersect at a point. And then another 2 of my 4 given lines intersect at another point. Well, now the problem's not so hard to solve, because if I want another line that passes through all 4 of them, I can easily just connect these 2 lines, right? Or these 2 points. And now, of course, that red line, I'll just draw it red, passes through all 4 of the yellow lines. And then, is that it? Anybody see other solutions? The one where the planes intersect, right. So you can draw the plane containing these 2 lines and the plane containing these 2 lines. And these 2 planes are going to intersect down here in some other red line. And that red line, since it's in the plane of both these yellow lines, it intersects all 4 of those yellow lines. And that's actually the only 2 solutions you can have in this case. It's not so hard to see. So then Schubert, being back in the 18th century when math wasn't so rigorous, said something like, well, look, it's 2 in this case, and like if you pull apart the lines a little bit by continuity, like there's sort of a principle of conservation of number, and the answer is always going to be 2. and he just sort of claimed it, right? There was a lot of mathematicians who did these problems this way, and they ended up making mistakes for harder problems like number 5. So how many k-dimensional subspaces of C to the n intersect each of k times n minus k subspaces of dimension n minus k non-trivially? I don't know, right? So we'll answer this as the course goes on. So that's, this is one of our goals, is to answer question 5. So this stuff needs to be put on a more rigorous foundation. And actually, Hilbert's 15th problem was to put this sort of method of principle of conservation of number on a rigorous foundation. I also want to point out why I'm working in C here. If I change this to R3, actually sometimes the answer could be 1 or 0. Because basically, this problem itself isn't so hard. You could set up the equations for these lines and try to, figure out what the possible solutions could be for the red lines. You get some quadratic equation, basically, which has 2 solutions over C, but it might have 1 solution over R or something like this. Okay. Okay, so the idea of modern Schubert calculus now is to take the 4 yellow lines. Let's draw them in general position now. So let's take 4 lines. Imagine these in 3 space, so they're crossing each other somehow. Okay, so let's call these L1, L2, L3, and L4. And what we're going to end up doing is making Schubert varieties. Which are defined to be the sets of all lines passing through each of these lines. So we're going to define omega 1, say, to be the set of lines passing through L1. And we're going to see that this has the structure of an algebraic variety. There's a topological structure on omega 1, lots of nice things. And we're going to do the same thing for each of these lines with omega 3 and omega 4. So you imagine all the lines passing through each yellow line, and now if we intersect these sets, then the answer should be in this intersection, right? So we want to compute the size of this intersection, and we want to show it's 2, always, right? No matter what L1, L2, L3, and L4 are. So that's the general strategy. Is we want to define what these Schubert varieties are, and then compute their intersection. So to do that, I mentioned I don't like parallel lines not intersecting. So we're gonna back up and go over some basic stuff about projective space and projective varieties. It might be a review for some of you, but I think there's some undergraduates in here. So we're going to talk about projective space, which fixes parallel lines. Projective space and projective varieties. Okay, so here's the idea of projective space. Imagine you're standing on parallel train tracks and you're looking out toward the horizon. They're going to look something like this, right? So here's my horizon, and there's the train tracks getting farther away. Well, the parallel lines actually meet out at infinity, right? So in projective space, that's what we're going to construct. Or in the projective plane, at least. Meet at infinity. So how do we define projective space? Well, we're actually going to define it first in a sort of abstract way as the set of lines through the origin in a higher dimensional space. So we're going to define Pn over a field K, which could be C or R or whatever you want, to be the set of points. So we're going to define it as a quotient space where you take all non-zero points, x0, x1, through xn. So in k to the n minus 0, 0, 0. And then we're going to mod out by the equivalence relation given by scaling multiplication. So x0 up to xn is the same as y0 up to yn if there's a non-zero element of the field such that x sub I times a is y sub I for all I. Okay, so it's just you take your, so why is this lines through the origin? If you take a higher dimensional space, k to the n, and you take, you remove the origin, and then you consider the equivalence class of take a point out here and all its scalar multiples as one equivalence class, well, that's a line passing through the origin. So the points of Pn are lines or one-dimensional subspaces in Kn plus 1. Okay. Okay, and then if so if K is a topological space, like say K is C or R, then C has a topology, and we can take the quotient topology here to give Pn a topological structure. So now we can talk about open sets. So basically a set is open in Pn if its corresponding union of equivalence classes here is open in the higher dimensional space. So there's your open sets. Okay, so let's think about what this actually looks like. So here's, let's draw P1R. Oh, and I forgot to mention that, maybe I'll start P1R over there. Here's another notational thing. Since basically our points are just up to scaling, we're going to write x0 colon x1 colon x2 up to xn for a point in projective space coming from x1 through xn. And it's basically because they're ratios, right? That's what the colon is for. So okay, so let's look at P1R, because this one's easy to draw. So this is the set of x comma y, or x colon y. X and y are not both 0, so I could write it as this if we want, where x and y are real. And we want to think of this as lines through the origin in R2, but we want to think of it also as a one-dimensional projective space. So the way we do this is, here's R2, and we're thinking of these points as equivalence classes of sort of slopes in R2. But if we take the line y equals 1 here, and we sort of intersect each of our points of projective space, which are lines in R2, with this line, we get a sort of canonical representation of almost all of our points. So, for instance, if we had the point, I don't know, 2, 3, maybe that's 2, 3, then it intersects the y equals 1 point. If I think of it as 2 colon 3, well, that's the same point as 2/3, 1. And that's the one we want to think of as lying on y equals 1, right? So basically, for almost all of our points, we can scale down both coordinates so that y equals 1, except for the horizontal line, the x-axis, which is y equals 0, and you can't divide by 0. So there's nothing you can do with this one. This one doesn't intersect this line that it's parallel to. And so that's going to be the point at an infinity. This is the point that can be represented by 1 colon 0 in projective notation. So how does this look topologically then? Well, basically, you have this open set corresponding to this line. So topologically, it corresponds to this this line that sort of, as you move the lines closer to horizontal in either direction, it gets closer to infinity, which means the line actually wraps around to a point at infinity here. And so abstractly, as a topological space, P1R just looks like a circle, right, with a point at infinity wrapping it all up. So in some sense, a projective space is a compactification of an affine space. So this is R1, affine R1, and then we close it up into projective space with an extra point. Now, it's like kind of interesting. Over R and C, things look pretty different. So P1C looks almost the same, except instead of attaching R to a point at infinity, we attach C to a point at infinity. And attaching C all up into a point kind of looks like a sphere, right? Some kind of balloon that's just sort of pinched at the bottom. So that's the Riemann sphere. Okay, let's do one more example. Let's do the projective plane P2. And if I drop the subscript, I mean, it really doesn't matter, and I'm sort of treating it abstractly, or maybe it means I'm over C, because I'm usually over C. So let's say I'm over C. Let's write it as, I'm just going to write this. But sometimes I'm going to draw my pictures as if they're over R to indicate, like, the number of coordinates. So let me know if it's confusing. All right. So basically, what does C consist of in this sense? Well, again, we can do the same trick. We can think in 3 dimensions and then intersect with the z equals 1 plane. And what happens there is now our lines mostly pass through the z equals 1 plane, except the lines that are in the xy plane. And these guys don't intersect there, but there's a whole projective line of those. So what the structure is you have a projective line at infinity, and then you attach a whole extra plane to that somehow. And the attachment is a little bit funny because in terms of how things are actually wrapped up, it's easier to draw it like this. People usually draw a projective space where we take a square and we kind of identify opposite edges, and then we attach a sort of disk on like that. And I'll talk more about CW complexes in a second, which will make this all more clear.
That's more of a real picture.
Yeah, right. This is our, yes. So we do, yes, you're right. I was trying to get away with things that I'm not able to get away with. All right, so let's do P2R for now. Okay. You can still talk about the different patches, a z equals 1 patch in any projective space, which actually, let's talk about that now. So affine patches. So this setting one coordinate equal to 1 kind of covered a lot of our space. And so the ith affine patch, we're going to define AI to be the set of points of the form x0, x1, up to where the ith coordinate is 1. So we have xi minus 1, 1, I plus 1, and so on in Pn. So that's the ith affine patch. And these actually form an open cover of projective space. So for instance, in P1, is this too low, by the way? Can you guys see this circle? Maybe I'll redraw it. So in P1 R, we have our point at infinity here, and this is our affine patch y equals 1. This is x colon 1. But then we can also cover it by instead looking at the point 0 here, which is 0, 1, right, in the affine patch. Because we're thinking of x1 as a line just by ignoring the 1. And then taking the affine patch x equals 1, and that includes infinity down here. This is the points of the form 1 colon y. So the orange open interval and the yellow open interval kind of cover, giving you an open cover. projective space. So that does mean that projective space is always compact, and so it is really a compactification of one of the affine patches, which is just Euclidean space. So, okay, so now let's talk about varieties, which Schubert varieties are. So an affine variety, you've probably seen before, is it's a zero locus of some set of polynomials. So you have polynomials in n variables, f1 through fr, say, and we define v, the vanishing set of f1 through fr, to be the set of points, say, if we're working in n variables. So this is an affine variety in, some field to the nth power, such that each f vanishes on them for all I. Okay. So you guys know how to draw affine varieties. For instance, if fxy is y minus x squared, then when is f of xy equal to 0? Well, it's when y equals x squared, right? So the vanishing locus of f is just this parabola. This is v of f. So that's an example of an affine variety. Another example, which we're going to use when we look at these Schubert calculus problems, is k-planes. So that was an example of just one function, but we can intersect two polynomials. So say f of x, y, z is x minus z, and g of x, y, z is x minus y or something. Then the vanishing locus of f and g is the locus of all points on which both of these functions are 0, which means this is the locus of points where x equals y equals z, right? And what this is doing is, in 3 dimensions, we have, if we just take the vanishing locus of f, we get a plane, x equals z. I'm not going to try to bother trying to draw a plane on the board, but we have some plane x equals z and some plane x equals y, and then their intersection is a line. And so what we're really doing here is we're sort of intersecting the vanishing loci of f and g. And in general, that's what you're doing. When you have multiple polynomials, you're kind of intersecting their graphs of the 0 locus. So so that's the idea of an affine variety. And then for a projective variety, we want to take the same thing, but we have to be careful about what our polynomials are. So I went a little bit too far over here. So projective variety in projective space is just the vanishing locus of a number of homogeneous polynomials in the variables defining the projective space. Okay, why does it have to be homogeneous? What happens if I take f of xy is y minus x squared, and I try to define this on projective space, which really means I'm taking x colon y. So what goes wrong here? Can somebody tell me why this doesn't define something well defined? If I try to take like the set of all points x colon y for which this is 0. Yeah?
Scale, if you multiply by 2, then it doesn't work anymore.
Exactly. So if we take a solution of this, like 2 colon 4, because 2 squared is 4, so that makes this equal to 0. Well, this is the same point as, I don't know, 4 colon 8. but 4 squared doesn't equal 8. So it's not even well defined, like what it means for this z0 on a point. So it is well defined, though, when all of the polynomials have the same degree, because then if you scale all the variables, everything goes up in the same amount, and scaling 0 is still 0. So, so how can we fix this? Well, our mistake was really, this is an equation in the affine plane, and to make it an equation in the projective plane, we want to just add another variable, because the projective plane actually has 3 variables, and we think of z equals 1 is when it's just the 2-variable plane. So what we want to do is add a z in here somewhere so that it's homogeneous. So I can just stick one in front of the y, and now it's degree 2. Right. So this process is called homogenization. So the homogenization of a polynomial f in say x0 through xn minus 1, you can actually, it suffices to use one variable, so say by the variable xn, is the unique polynomial, is the unique homogeneous polynomial g in x0 through xn, such that, so g is homogeneous of the same degree as f, and basically we want, so if we want that if we plug in z equals 1, we get the original polynomial back. So we want that g of x0 up to xn minus 1 and then 1 is the same as f in the first variables. Okay. So this is an example. Let's do one more example of a homogenization. So let's do, I just made up this nice example here. Okay, so there's a polynomial that's not homogeneous, and we want to homogenize it with a third variable z. So if this is f, then g would be, so first of all, what's the degree of this polynomial? It's 5, because this is the highest degree. This is degree 3, and that's degree 4. So we need to raise this degree 3 thing with some power of z. So we need 2 z's in order to make it degree 5. So we do x squared y z squared. And then x to the 5th can just stay x to the 5th. And then we need to raise this using 1z. And now everything's degree 5. So this is the homogenization. And of course, if you plug in z equals 1, you get back to it. Okay, so the cool thing now is that this has a nice geometric meaning, this homogenization. It's basically taking the projective closure of an affine variety, thought of as living in an affine patch of projective space. So, so the cool thing is, say we take our parabola, which was defined by y minus x squared, but now let's think of this as the affine patch z equals 1 in the projective space in which we have a line at infinity here, and actually an extra point at infinity, right? This is going to be the points of the form x1, 0, and this is going to be the point 1, 0, 0 in projective space. Everything else is x, y, 1, right? And the question is, what happens if we now consider its homogenization, which certainly has the same zeros in this affine patch, but we add a z, and now we can think, well, what are the zeros of the form x1, 0 or 1, 0, 0? Which of those satisfy the homogeneous equation? And you can check that basically only this one. No, sorry, wait. I drew this somewhere wrong. I think oh, no, not this one. It's, yeah, it has to be up here. Yeah, so it's when, I just can't think on the board. 0, 1, 0 should satisfy this, right? I know it does, even though I can't like compute it because I'm at a board. All right, so 0, 1, 0. Yeah, makes that 0. And nothing else does, and you can check that. So the point is that parabolas kind of, if you follow them way off to infinity, they actually go to a point way up there, like in the closure in projective space. And so I don't actually know if this is true, but we talked about when you're on a train track and you look at the parallel lines, they kind of meet at infinity, right? I think it's true. Like I was trying to imagine it, but I think if you're standing on a very flat plane and you see a parabola, right, then I'll try to draw it to make it look like our other diagram. Let's draw train tracks on it that are getting closer together. I mean, okay, the point is it should look like an ellipse. And I don't think I've ever seen this in real life, but it should happen. I mean, of course, it's not actually at infinity, but like that's what your eye would see. So that's what a parabola, I mean, it's kind of unintuitive that these sides of the parabola would actually get closer together, but the point is that their derivative is sort of getting so high that they're almost straight eventually, and then that's like parallel lines again, and they do start getting closer together. So anyway, yeah.
Salt lake. On the salt lake.
On the what?
Close to Salt Lake City.
Salt Lake City, right. Well, I almost want to try this now. Like I thought of this when I was making these lecture notes, and I'm thinking, man, I really want to draw a parabola on the sand now and just stare at it. So
we'll ask for money. Everyone together and somewhere.
Yeah. So anyway, this is a fun picture. So one of the cool things about projective space is actually that all conics are essentially the same, up to different, what's called a projective transformation. I have things about projective transformations in the notes. I don't think they're really essential, so I'm not going to really cover them. But we can, just to give you an idea of why a parabola really is the same as an ellipse or a circle or a hyperbola in projective space, is that we can just look at this picture, zy minus x squared, in different affine patches. And actually, it's easier if I translate it up first. So if you don't mind, I'm going to change my equation. Let me get rid of my ellipse here. So let's actually consider, instead of y minus x squared, let's shift it up by 1 so that when we send this line to infinity, it's not going to send a point to infinity. So let's do y minus x squared minus 1 as an affine variety. That's shifted up now. And now we homogenize, make the z squared, make it all degree 2. And so this variety, this equation equals 0, looks like that in this affine patch. But then if we take, so this is the z equals 1 patch. But if we instead take the y equals 1 patch, then we get z minus x squared minus z squared equals 0. And we can rewrite this, we can take it as, we can complete the square with the z and z squared. And that looks like a circle, right? So it actually literally is the circle with radius 1/2 in the y equals 1 patch. I don't know where it is, z minus 1 something. And then in the x equals 1 patch, this actually looks like zy minus 1 minus z squared in the zy plane. And I can factor this as, so I'm going to put the 1 on the other side and factor this as z times y minus z. And we all know xy equals 1 is a hyperbola. So this is just a transformation of a hyperbola. It looks like something. I don't know where the curves are. But basically, we're taking this parabola and just viewing it from different patches of the projective space, and you get all different kinds of conics from the same picture. Okay, so that's one nice thing about projective space. The main idea is it's going to clean up a lot of our work when we start going to those higher dimensional intersection problems, because you get such uniformity principles like this. When did I start? 11? And I have till 12:30. Okay, sounds good. Okay, so yeah, so speaking of Schubert calculus, let's go to K-planes very quickly. Let's just talk about what projective varieties they are. So then a k-plane can be defined by first defining a hyperplane in projective space to be the vanishing locus of a function where f is a linear polynomial. Say a0, x0 plus a1, x1, homogeneous linear. And then intersect n minus k of the hyperplanes, and you get a k-plane. So, so a k-plane in Pn is the intersection of exactly n minus k hyperplanes. So here each f sub I is going to be a sub I0, x0 up to whatever a sub I n xn, where these a sub I coefficients have to form a full rank matrix. That's the only thing we need to make sure. So rank k, or rank n minus k, I guess. So as long as they have that property, then they're going to intersect in the right way, and we get a k-plane. So now let's finally see why lines are parallel in the projective plane. Or sorry, parallel lines intersect. That's what I meant. Lines aren't parallel in the projective plane. So in P2, a line is a hyperplane, right? It's dimension 1, codimension 1 too. So a line is something like ax plus by plus cz equals 0. And then if we take two lines that are parallel in the z equals 1 plane, say like, 2x plus 3y plus z equals 0 and 2x plus 3y minus z equals 0. If you set z equals 1, these are parallel lines with different y-intercepts. And then they have to intersect at the point at infinity, which is going to be a point where z is 0. And whatever makes 2x plus 3y equals 0, the only ratio that does that is when x is minus 3 to 2 is the ratio. Right? So this is the point at infinity that it intersects at. Okay, so now that we've done that, let's go revisit our Schubert calculus quiz that you guys have. And in particular, problem 2, what I want to do for the rest of the mini course is think about all our Schubert calculus problems in projective space, because it just makes the answers much more uniform. And we don't have to worry about, oh, are they parallel or are they not? Right? So for instance, problem 2, if we rephrase it as how many lines, how many points, how many points are in two distinct lines, right? Well, now the answer is B, right? That it's, where was it B? Whatever it was. It's B. Yeah, because it doesn't depend on the choice of lines, right? Right, so I'm going to change this problem to how many distinct lines in P2, right? And now the answer is B, just one. Okay, so think of the prime, 2.2 prime says this. Now, when we get to Schubert calculus, it's also going to be actually helpful to think of this, now that we've projectivized, think of it as an affine problem in one higher dimensional space. So this is a very important concept. Remember, we defined P2 initially as the lines through the origin in C3, right? So this is P2C. We're going to stay over C now. So we can also translate this problem again. Let's say 0.2 double prime or something is our second problem. And we can say, if we go up to C3, so again, a point in projective space is a line through the origin in C3, and I'm going to call a line a one-dimensional subspace. How many one-dimensional subspaces say V in C3 are contained in each of two distinct somethings. So what's a line now? What does a line become when we go up one dimension? It becomes a plane through the origin, right? Because it's sort of determined by 2 points, and then it's a plane is determined by 2 vectors. So in 2 distinct 2-dimensional subspaces, say W1 and W2 in C3. So the answer is also obviously 1 here, right? It's a central problem now. It just makes everything nicer to think of it as subspaces rather than floating off in space, not attached to the origin anywhere. Right, so now, I mean, you have your origin, you have 2 planes passing through the origin, and you have your line through the origin contained in them. So now everything's sort of a central arrangement instead of just out in space. So let's do the same thing. Since this concept is so important, let's do the same thing for problem 4. So let's look at point 4 and make it point 4 double prime, where we're going to projectivize and then go up 1 dimension. So problem 4 said, I'm going to get my sheet out here, how many lines intersect 4 given lines in C3? Let me rewrite it here so we can just translate it one step at a time. So how many lines intersect 4 given lines in C3? So let's change this to P3. That's an easy step. We'll make it point 4 prime. Where no 2 of the 4 given lines are parallel or intersecting. Let's leave that condition for later. Let's just look at what it looks like when we go up 1 dimension. So now we're going to be in C to the 4th. We're actually going to be in 4 dimensions and considering things through the origin. A line, again, becomes a 2-dimensional subspace. So how many 2-dimensional subspaces V intersect each of 4 given 2-dimensional subspaces? So this is in C4. Say V1 through V4. Except we have to be careful about intersect as well. So here, pass through is a little bit funny because everything intersects when you're central, so that can't possibly be the right thing, right? Everything intersects at 0. What is going on is passing through at least a point, or coinciding as lines, corresponds to passing, like the subspaces actually crossing in dimension at least 1. So we have to say such that dimension of V intersect VI for each I is at least 1. So that's, not something that all 2-dimensional subspaces do in C4. There's enough room for them to just meet in a point, but it's saying that each of them meets in a line or more. And then there's that extra condition, which I'll leave you to translate. And in fact, one of the problems in the lecture notes is translate all the other problems in a way to affine space in this way. Okay. That's good. So that's actually basically, so that my lectures are different lengths in terms of the sections 1 through 5. And I think sections 1 and 2 are going to be faster, and section 3 is going to be a lot longer. So we're going to actually start on section 2 now, which is Grassmannians. Any questions so far? chalk tape's disappearing. There it is. Okay. Okay, so why did we translate it like this? Well, now we can work in what's called a Grassmannian, which the projective space, the reason I spent so much time on projective space is the Grassmannian is just a generalization of this. So we're going to define the Grassmannian GR of n comma k to be as a set, the set of all k-dimensional subspaces of C to the n. Okay, now I've dropped all pretense of ever working over R. R was just to draw pictures. And now we're going to be working over C for the rest of the course. Okay, so this is very similar to how we defined projective space at first. We defined it to be the set of one-dimensional subspaces of some other space, right? So in fact, GR of n1 is p to the n minus 1, right? Because we had that other notation. So how do we think of the Grassmannian? Well, we want to put a topology on it like we did for Pn. So we want to think of it as a quotient space. So we're going to think of a point as, so point in the Grassmannian can be represented as as the row span of a k by n matrix. Some k by n matrix. So just, k vectors generate a k-dimensional subspace. And then we can ask, what are the relations that we can apply to, we can certainly scale rows and it doesn't change the subspace. Turns out elementary row operations also don't change the subspace, right? Because they're just linear combinations. And so we can basically define it to be the set of all these matrices modded out by elementary row operations. So yeah, let's just define this to be. So it's basically c to the, I don't want to say c to the k times n. I guess I want to say full rank matrices. Oh yeah, these have to be full rank as well to be dimension k. So let's just say full rank k by n matrices, which is some subset of the space of k by n matrices, mod the equivalence relation given by just generated by elementary row operations. Which means we can, scale a row by a non-zero factor, add rows to other rows, or change the order of rows. Okay. So what this means is we can actually do a similar thing to affine patches, but for the Grassmannian. So let's do an example of what you've all seen before, which is basically row reduction to get the matrices in a certain canonical form. So I made a really easy matrix to row reduce. So let's work in GR 7, 3 as an example. Okay, so I'm just going to row reduce this in a way that I wanted to get it so that the pivots are actually traveling up and right. And the notation is going to be so that we end up with partitions and combinatorics in the end. So just to be clear on what I'm doing, I'm just going to do this one quickly. So basically, we can add this row to this row. Actually, maybe I'll just skip the whole thing. So I'm going to add this row to this row. A lot of stuff's going to cancel. We're going to get a 1 in this position. And we can, cancel make the zeros in its column. I'll skip to almost the last step. So then this 3 doesn't go away. This guy ends up being our next pivot. And we can clear those rows. and we end up getting something. Okay, and there's our last pivot ends up being here because I made it so that everything cancels. So the point is we want to order these rows so that the ones, the leftmost ones in each row are moving up and right. So I'm going to write this as the one with the most non-zero entries first on the bottom, and then the one with this guy. Okay. And I'm going to warn you that if you read about Schubert calculus in the literature, everybody has a different notation for how they do their row operations, and it all makes a lot of difference, but I like mine the best, and we'll see if it works. So the point is that this, what I want to focus on is the positions of the ones here. I want to think of this actually as just living in a subspace of the Grassmannian whose canonical form, whose row-reduced forms like this, just have this format with the ones there, and then we don't know what these starred entries are. They could be whatever you want. But this is in this set. And this kind of set is called a Schubert cell. Okay, so the Schubert cells are sort of like the decomposition that we had, where we'd have, you know, the plane and then a line at infinity and then an extra point at infinity. There's going to be a decomposition of that sort of form. In fact, let's see what the Schubert cells are in Pn. So row reduction in Pn is just, now we're thinking of our matrices in canonical form as you see where the leftmost one is. Well, maybe it's here, and you have a bunch of stars. Or maybe you have a zero entry, and then the first thing you can change into a 1 is there. And this looks familiar. We were doing this kind of thing in Pn, except we were writing colons instead of matrices. It's the same thing. So there's 4 Schubert cells that make up P1, and they cover P1 just like these do. Okay. Okay, so before I go on here, so we're going to talk about Schubert cells and then close them to get our Schubert varieties, and the Schubert varieties are exactly what we wanted to intersect for our Schubert calculus quiz. But I want to talk about why the Grassmannian itself is a projective variety. So let's see. Maybe I can erase this, yeah. So there's a cool embedding called the Plücker embedding, which embeds this in basically n choose k dimensional, or n choose k minus 1 dimensional projective space, which is just formed by taking your matrix and labeling your rows up to 1 through n, and then taking the coordinates of this projective space, so the Plücker coordinates, it's called, is x sub s for s, a subset of 1 through n, is you just take some of the columns and you take the k by k submatrix and you take the determinant of the k by k submatrix determined by s with columns s. So this gives you n choose k coordinates, which you notice that if you do elementary row operations, you might scale all the determinants by the same thing, but you'll never, it'll be in a homogeneous way. So that's why you get a well-defined element of projective space from this. So we'd have all these elements, xs1, xs2, right? These are our Plücker coordinates for different subsets, n choose k. And that's the Plücker embedding. Now, why is it a variety? There's Plücker, what's called Plücker relations, which I don't personally use much, but it's worth mentioning because the first time you learn about a Grassmannian, it's worth seeing. that it actually is a variety itself. But the Pluker relations are basically just the defining equations of this as a variety in this higher dimensional projective space. So there's some combinatorial exchange relation that defines the Pluker relations. I'm going to just refer you to the book Ideals, Varieties, and Algorithms by Cox, Little, and O'Shea. It's one of the references in the lecture notes. They do a great job explaining where the Pluker relations come from and how you can derive them and some of the commutative algebra behind that. But let me just give you an example of one. In our 3×7 case there, we can have the set x 1, 2, 3 times x 2, 4, 7. So these are the coordinates indexed by those. So those determinants, it turns out, always satisfy quadratic relations, where this is a sum of other products where you end up switching some of these entries in a certain way. It turns out to be equal to, let's see, x 1, 2, 4, x 2, 3, 7 minus x 2, 3, 4, x 1, 2, 7. So you see we're kind of using the same coordinates in some permuted way, and there's an algorithm for generating all these relations that cut out the Grassmannian. So I thought it was just worth mentioning. I'm not going to go into it in too much detail. Yeah, sure. Right, or this is a function, right? And then we're going to take the vanishing locus of all those functions. Yeah. Okay, so let's go. Now I want to talk about, we've interpreted this as a subvariety, which is one way that the Grassmannian, has an algebraic and geometric structure. We've also talked about it as a quotient space, so it inherits the quotient topology from quotienting out by elementary row operations. And now I want to talk about it as a union of Schubert cells and what's called a CW complex, which we're going to end up using later. So maybe I should just keep the Schubert cell up for now. So what I want to do is now finally get into some combinatorics that's associated to Grassmannians. And Stephen actually just defined partitions for me this morning, so I don't need to define the partition. Maybe I'll just remind you very quickly, lambda is some sequence of non-increasing positive integers. It's a partition. And we're going to write size of lambda to be the sum of the parts, and L of lambda to be the number of parts R. And then the Young diagram, I'm unfortunately going to use different notation from this morning. I am going to use English notation, which he kept trying to write. And so let's do the example. If lambda is 4, 2, 1, then I'm going to draw 4 boxes in the first row, and then 2 in the second row, and 1 in the last row. And I actually really prefer French notation. I really do. But a lot of my favorite references in Schubert calculus, including this book that I carry around with me religiously everywhere, it's Fulton's book on Young tableau. It uses English notation, and so it seems like the literature on Schubert calculus is more English. So we're gonna use this notation for the talk. Okay, but actually my notation is flipped a little bit from Fulton's notation in his book, because my matrices are actually backwards. So beware when you read other books, they might be different. Okay, but we want to associate a partition to a Schubert cell in a unique way. And the way we do that is, notice these positions of the ones is what we're worried about. And we're just going to look at how far they can't be in the same column. So we basically shift them over by one column each and then see how far they are from the left. Another way of saying that is cut out a staircase from the left. Okay, I'm just going to ignore these zeros over here. And now the distance from the staircase boundary to these ones is going to be the partition that I assigned to this Schubert cell. Okay, so you can almost see the partition. I'm just going to shift it over. So that so lambda is my 4, 2, 1 here that I assigned to this Schubert cell. And I'm going to write this as omega lambda circle. is the Schubert cell corresponding to lambda. Okay. So let's see where these partitions lie, because you can't get just any old partition from this. In GRNK, turns out there's a very important rectangle that they all fit in. So if lambda, say, indexes a Schubert cell in GRNK, well, we know a few things about lambda. First of all, the number of parts of lambda is certainly bounded by k, right? This one could be all the way over to the left, in which case that last part is 0. So you can't have 0 part. It could be that you don't have all k parts, but we know that the length of lambda is less than or equal to k, and we also know that the longest part, the top part here, its longest possible is n minus k, right? So because we shifted it over like that. So lambda 1 is less than or equal to n minus k. And another way of, an equivalent way of saying these two conditions is that lambda's Young diagram fits in a k by n minus k rectangle, right? So it's some diagram like that. And this rectangle, I'm going to refer to it so often that just for the purpose of this mini course, I'm going to call this the important box. This is not standard notation. Okay, but we're always going to refer to this as the important box, because we're going to do so much combinatorics in here, it's going to be unbelievable. So, all right. Oh yeah, so one nice thing about the important box is it gives us an easier way than this stupid shifting and cutting out staircases way of finding out what our partition is. You can actually just take these stars that we drew, whatever your asterisks are in your Schubert cell, and make your important box. So what is our important box over here? K by n minus k is 3 by 4, right? And we just take these asterisks and shift them to the, align them to the right, get rid of any zeros in between, draw the partition shape that they form in the lower right-hand corner. So it's an upside-down partition shape, which is another, not French or English. But then the complement is our 4, 2, 1. So whatever is left is lambda. Okay. So that gives us an easy way of seeing what the partition is. Okay, so let's finally. I've been using a lot of pictures here. Let me algebraically define the Schubert cells and then the Schubert varieties. So omega lambda open can be defined as the set of V and GR NK, so the set of points on the Grassmannian, such that the dimension of V intersected with the span of the first R basis vector. So we're choosing a basis here, E1 through En, and actually, so one unfortunate thing about my notation, I chose my notation so that the partitions in here would be really easy to do combinatorially, but I'm actually defining E1, E2, my basis elements are going backwards. So like this vector 0, 0, 0, 1 is actually E1, and then E2 is going to have a 1 in the next to last position. No matter how you flip things, something's going to be bad, and this is what I chose to be bad. So, okay, so with that notation, this is this condition is that this intersection is I whenever R is between n minus k plus I minus lambda I and n minus k plus I minus lambda I plus 1. Okay, so it's quite a mouthful, but we're going to generalize this pretty soon, and it's going to be easier with this formula. So, oh yeah, let's talk about the dimension of a Schubert variety as well. So, or sorry, of a Schubert cell. How many copies of C do we have? Well, it's the number of stars, and that's the complement in the important box of our partition, which is C to, so it's going to be k times n minus k is the total number of boxes in our important box, and then we subtract the size of lambda. So that's worth knowing is sort of the dimension of the Schubert cell. And now, finally, we get to define Schubert varieties, which are the same dimension, but they're the closures. So here's the big definition. A Schubert variety which I'm going to write as omega sub lambda with no circle, is defined to be the closure of the Schubert cell in the Grassmannian. Okay, now that's fairly abstract. So one way we can define it, which I'm going to have you check in the exercises that this is true, is that given this definition, which corresponds to just where those ones are, you can check that it's the set of V in the Grassmannian such that the dimension of the intersection of V with E1 up to, now we just use this formula in here, up to E n minus k plus I minus lambda I is at least I. Okay. So that turns out to be what the closure is. Let's talk a little bit about closure. Actually, I didn't really talk about closure in the projective space, except for like the pictures. But what this looks like if we're going to close up a Schubert cell in P1, so go over here so you can see. Let's do the Schubert cell omega sub 2 boxes in, let's say, P4. I think I want. Sure. So in P4, we have 5 coordinates, and the 2 boxes indicates that, well, the codimension is going to be, oh yeah, P4, let's actually think of it as a Grassmannian. That'll make it easier. Grassmannian of 5, 1. It's 1 planes in 5 space. So this Schubert cell looks like all the points of the form 0, 0, 1, yeah, okay, see, I have to do this with the important box. The important box is 1 by 4, and the partition lambda is 2 squares, and so I have 2 stars. So that's the easy way, is figure out where the stars are, and then just put them in there, and then everything else follows. Okay, so this is what that Schubert cell looks like in P4. And then its closure is going to include, so in, sorry, this is the open Schubert cell. And if we close it up to the full Schubert cell, this is also going to include things like this. So this smaller Schubert cell, omega 3 boxes. Sorry, add a box. Okay. Because if I set this variable, this star, if I take it to infinity, then I can make this ratio be almost 0 to 1, basically. So that's why in the closure you get this extra point. And you also get the points of the form 0, 0, 0, 0, 1. And so to summarize, I mean, we have this interesting thing that's happening is the Schubert variety is actually a union of Schubert cells. So we have omega sub 2 in P1 in P4 is the union of its open set, which is dense in that closed set, union with omega 3 boxes, open, union omega 4 boxes. So somehow these Schubert varieties, when you take their closure, they kind of union a bunch of smaller Schubert cells formed by adding boxes to your partition that you started with. And I also have an exercise in the notes of seeing, like, given any Schubert variety, seeing what Schubert cells are in its closure, which is a fun exercise to do. Oh, right. So now is the exciting part, which we're getting just to at the end. So what is omega box in GR42? Okay, why am I doing this? So going back to the Schubert calculus quiz, that problem that we started with 4 lines in 3 space and lines passing through them, we translated it into an affine problem about 2-dimensional subspaces passing through the origin in 4-dimensional space. So that's why I'm going to consider GR42 now, because we're going to consider 2-dimensional subspaces of C4. And I claim that this Schubert variety is what we need to solve our problems. So let's just write it out with. So this is the partition lambda equals just 1. So it has 1 part. And using this definition, we can write this as the set of 2-dimensional subspaces, so V and GR42, such that the dimension of V intersect. Now we have to figure out what this thing is, n minus k plus I minus lambda I. So here n minus k in this case is 4 minus 2, which is 2. And then I, the only I we have for lambda sub I to exist is 1. So in general, the number of these inequalities we have is the number of parts of the partition. And then here I just is 1, and lambda sub 1 is 1. And so we get 2 plus 1 minus 1 is 2. So we get just the first 2 coordinate vectors is at least 1. And that's the only condition we have. So this is saying that this Schubert variety is telling us all the 2-dimensional subspaces that intersect a fixed 2-dimensional subspace in dimension at least 1. So that's what we wanted, except we had not just one given subspace, we had 4 different given subspaces. And so we need to somehow change our basis and define a different Schubert variety decomposition of the Grassmannian in order to intersect them and get what we want. So for this, we need what's called a choice of a flag. So it's not just a change of basis. What we really want is a chain of subspaces. So here's a definition. A complete flag in Cn is a chain of subspaces that are all contained in each other. Actually, sometimes 0 is called F0. Let's do that for rotational purposes. Where each dimension goes up by 1 each time. So dimension of F sub I is up. And the reason one reason it's called a flag is that 0 is just a point, and then F1 is a line, and then F2 is going to be a plane containing that line, which you can think of as a little flag. And then F3, say we're in C3, and then we're all done. So this is an example of a flag. Okay, so a chain of subspaces like this, one classical example which we've been working with is, this is called the standard flag. So we have E1 contained in, E1, E2, and then up to the whole thing. And so we've been intersecting our points of the Grassmannian with elements of some of the standard flag. But in general, we want to generalize the definition of Schubert variety to any flag. So maybe let me just generalize it right over top of the definition. So Schubert cells actually as well can be defined as, I'm going to put F here. oh yeah, I usually write F sub bullet to be the whole flag of subspaces. And then you could say omega lambda of F is the set of all V for which V intersect the rth part of the flag is this for R satisfying these conditions. And then same thing for the Schubert variety. So we're just going to replace this guy with F sub n minus k plus I minus lambda I. And we're going to write omega lambda of F. And this is the closure of omega. Okay, so now we can talk about the different flags that we needed. So now we write omega box of some flag F bullet, and this is the set of V such that dimension of V intersect F2, and I'm labeling this flag with a 1 because I'm going to use 4 of them in at least one. And now we can just choose 4 different flags with, importantly, 4 different F2s, and we can take the intersection of 4 of these. And this is the intersection that we want to show is 0-dimensional and has 2 points for all choices of flag. Okay, so I have 5 minutes here. So that's not enough to go into the next thing. So let me just talk about the conditions on which these intersections are nice. Yeah, so the choices of flags, I mean, in this case, we really just needed sort of 4 distinct F2s. Oh, but actually, in the Schubert calculus quiz, there is a condition on problem 4 that says no 2 of the 4 given lines are parallel or intersecting. And that's basically saying we want these F2s that we pick to all be sort of transverse. We don't want them intersecting in a line, because otherwise we might get sort of degenerate things happening. So let me talk about what transverse flags are. So we say 2 subspaces V and W in C to the N are transverse if their intersection is the dimension you expect. So if the dimension of V intersect W is, let me get this right. So the codimension basically adds, and then whatever that means is is what transverse means. Right, so n, that's what I was missing. N plus the dimension of the intersection is dimension of V plus the dimension of W. Okay, so another way of saying this is that if the codimension is n minus the dimension, then the codimension of V plus the codimension of W is codimension of V plus W, which is what you would expect. And so we expect those F2 things to intersect in just the origin. And we say 2 flags are transverse. Say we have F and E if each piece of each flag intersects transversely. So. Okay, so I guess I'll end today by saying that this is really the condition that we want for the principle of conservation of number that Schubert wanted to use so haphazardly to be true is you want your flags that you choose for your Schubert varieties to intersect transversely. And that's the general, that sort of ensures that the intersections are what you would expect them to be. So I guess I'll stop there.